On the Rockin' World of Geology Program 1, the Standard Deviants take a closer look at the planet Earth. We'll learn a little about the Earth's past, cool geologic principles, and we'll even expose the secret lives of rocks. We'll give you all the geology knowledge you'll need to impress your friends and amaze your relatives. So whether you're a rock star or a rockhead, you're guaranteed to dig the Standard Deviants approach to geology.
It's pop quiz time. See if you can answer this. How old is the Earth? Is it A, 1 billion years old, B, 4.6 billion years old, C, 7.4 billion years old, D, 10 billion years old? We'll give you the answer after the show.
The Standard Deviants present The Rockin' World of Geology.
Starring Brad Aldous, Galila Azrez, Herschel Bliefeld, Jeremy Clavens, Tessa Monroe, Dana Rubinson, Gabrielle Smith, Malcolm Smith, Shannon Ward, and Jazz Maston.
Hi, I'm Tessa Monroe, and welcome to the Rockin' World of Geology, Part 2. So you want to learn geology? Well, stand in a doorway and brace yourself, because the Standard Deviants are about to rock your world. We've made tough geological concepts easy to understand. You'll learn all you need to know about metamorphism, faults, mountain building, earthquakes, the Earth's interior, plate tectonics, river and shoreline systems, glaciers, and much, much more.
Part 1. Principles, Materials, and Processes. Section A. Geologic Time. The Earth in Context.
Geologists study the Earth. Like doctors, geologists have specialties. For example, some focus on the oceans, others on the interior of the Earth, some even study other planets. Geology's many disciplines are separated into two broad categories: historical geology and physical geology. Historical geologists look at the formation and evolution of the Earth and life on Earth. Physical geologists study what materials the Earth is made of and what's happening on and beneath the Earth's surface. Most introductory geology classes focus on physical geology, so we'll do that too.
Now, when we talk about the time on Earth before humans were around, we're talking about a long, long, long time. I mean long, really long. You won't even believe how long.
Get on with it, man.
Sorry. Anyway, here's one way to think about geologic time.
If the first 4.6 billion years of the Earth's history were compacted into 1 year, the first forms of life would appear in May. The dinosaurs wouldn't be around until mid-December, and humans wouldn't appear until the last few hours of December 31st.
Humans have only been around for a few tenths of 1% of the Earth's existence. Hey, we're babies, infants, newbies, blips on the geological timeline.
Most of what you see in this video will show up on your exam in one form or another. Keep that in mind. But some of this information you just have to memorize because it's key to understanding trickier concepts. The geologic timescale is like that. Just memorize it, because once you're familiar with the huge scale of geologic time, you can fit events and concepts into that timeline, and the big picture of geology will make more sense.
By studying the rocks on Earth, geologists constructed a complete record that outlines the geologic periods of time when rocks were formed. There are two types of dating that geologists can use to construct timelines: relative dating and absolute dating. Relative dating does not assign an age in years to rock formations or geologic events. Instead, relative dating puts the events in sequential order. The oldest comes first, and subsequent events follow on the relative dating timeline.
At first, geologists only assigned relative dates to geologic time intervals, but more advanced dating techniques have allowed them to pinpoint the dates more exactly. Absolute dating assigns specific dates to rocks and geologic events.
Geologists study deep time. Deep time is the billions of years that form the Earth's history. Huge segments of time are broken down into eons, eras, periods, and epochs. We live in the Phanerozoic eon, which started 570 million years ago. Just like years are divided into months, weeks, and days, the Phanerozoic eon is divided into eras, periods, and epochs. Think of eras as being roughly like months. Periods are shorter, like weeks, and epochs are shorter yet, like days.
A period of time that we didn't include is the Bleem. A Bleem is longer than an era, but shorter than the eon. The proper use of Bleem would be as follows.
I ordered a pizza, but the delivery man still hasn't shown up. We've been waiting for like a Bleem.
Knowledge is power.
Prior to our Phanerozoic eon, there were 3 eons that actually account for most of the Earth's existence. They are the Pre-Archean, the Archean, and the Proterozoic.
We won't spend much time talking about them because most of what you'll study has happened during the Phanerozoic eon. But here's an overview. The first eon, called the Pre-Archean, began 4.6 billion years ago when scientists figured the Earth formed. Now let's translate that number to millions, since we'll measure most time periods in millions of years. 4.6 billion years equals 4,600 million years. So it's been 4,600 million years since the Earth was formed and the Pre-Archean eon began. 4,600 million is not quite as much as the number of burgers sold by McDonald's, but it's a lot of years.
The Pre-Archean eon was followed by the Archean eon, which lasted from 3,800 million years ago to 2,500 million years ago. Then came the Proterozoic eon, which lasted from 2,500 million years ago to 570 million years ago, when the Phanerozoic eon began.
There wasn't much life crawling around in the primordial muck during these eons, but there was some. The earliest fossils come from the Archean eon, dating back 3,500 million years. These were single-celled organisms, like bacteria, nothing you could hold a conversation with. The first multicellular organisms didn't appear until 700 million years ago, during the Proterozoic eon.
Look in your text for a complete breakdown of the eons, eras, periods, and epochs. Right now, we'll focus on the eras and periods, the months and weeks of the Phanerozoic eon, because chances are you will need to be most familiar with those time periods.
The Phanerozoic eon is divided into the Paleozoic, Mesozoic, and Cenozoic eras. Complex life forms have existed during these eras. The advent of shelled marine organisms established the beginning of the Paleozoic era, about 570 million years ago.
Earthling marine organisms.
They don't seem to be doing so well. Maybe we should do something.
Let's put shells on them.
That is a good idea. Let's do it.
The Paleozoic era is broken down into 6 periods: the Cambrian, the Ordovician, the Silurian, the Devonian, the Carboniferous, which can also be called the Pennsylvanian or the Mississippian. We'll explain what's up with that in a minute. And the Permian. So, what's up with the Pennsylvanian and Mississippian periods? Here's the deal. First of all, keep in mind that geologists distinguish each geologic period by its unique system of rocks and rock formations. The periods are generally named for the geographic location where the rocks of the period were first studied, or where the characteristics of that period's rocks are best displayed. The periods that aren't named for a geographic location are named for some special characteristic of their rock formations.
So here's the reason we list Pennsylvanian and Mississippian with Carboniferous. The name Carboniferous refers to the period between 360 and 286 million years ago in Europe. The name Carboniferous comes from characteristics of the rocks themselves, rather than the geographic location. We name that same period of time differently in the United States. We split it into two periods, and the names are taken from geographic locations rather than from the rocks themselves. From 360 to 320 million years ago, we distinguish the Mississippian period. And from 320 to 286 million years ago, we have the Pennsylvanian period. It is rumored that Uncle Sam himself instituted this American system of nomenclature.
It's the American way!
The first fish appeared 510 million years ago, toward the end of the Cambrian period of the Paleozoic era. Land plants didn't start to sprout until 430 million years ago, during the Silurian period of the Paleozoic era. Dinosaurs raised their little pea-brained heads 230 million years ago, during the Triassic period of the Mesozoic era, and they were joined by early mammals about 222 million years ago, also during the Triassic period. Luckily, the dinosaurs became extinct before the beginning of the Cenozoic era, 66 million years ago. The Cenozoic era is divided into the Tertiary period and the Quaternary period. The first horses appeared 53 million years ago, during the early part of the Tertiary period. Late horses appeared, well, later. Humans didn't show up until 4 million years ago, during the latter part of the Tertiary period.
Section B, Principles of Geology.
You probably know that geologists spend a lot of time studying rocks.
Study this hard rock, baby. Look at me. Look at the lights.
Geologists study rocks because rocks are like history books.
Ooh, history books. How exciting.
It is exciting. As the Earth has changed over the past 4,600 million years, it has written its story in the rocks.
Like graffiti.
So geologists learn to read rocks like history books. Most sciences have their own languages, so to speak. So get ready to learn the language of rock.
I wear pants. I'm a pants wearer.
Geologists call this library of rock history books the geologic record. The Grand Canyon is like one whole wing of the Library of Congress. There's a vast amount of information and history written into the cliffs and crags of the Grand Canyon, so, naturally, geologists have a field day there.
The canyon's layered beds of rock contain information about the Earth and its life forms from way back before we humans were around. For instance, even though the Grand Canyon sits on a plateau 7,500 feet above sea level, there are marine fossils in its rock beds. Pretty freaky, huh?
Geologists are Earth detectives. They collect clues from their observations of the geologic record and other stuff to figure out what happened in the Earth's past. Detectives solving crimes look for things like fingerprints and bloody gloves to lead them to answers. Geologist detectives look for specific clues in the rocks.
Sedimentary rocks give geologists many clues to what was happening on Earth when the rocks were formed, because sedimentary rocks contain little pieces of stuff that were around at the time of the rock's formation. Sedimentary rocks are made from sediments, things like little pieces of gravel, sand, silt, and clay, as well as the remains of animals and plants. Sediment gets carried around and left behind by water, wind, and glaciers.
Most sedimentary rocks come from sediments deposited on the margins of the ocean. As more and more sediment is deposited on the top, older sediment gets buried. This burial results in compaction and cementation. This overall process is called lithification, or the process of turning a sediment into a sedimentary rock. Often, plant and animal remains that were present in the sediment are preserved in the sedimentary rock. Scientists get pretty excited when they come across the preserved remains of some wacky prehistoric thing, because the remains are big clues to the Earth's past.
Rocks hold more clues than just the preserved plants and animals can convey. For instance, the way rock beds are situated in relation to each other and to the Earth tells a lot about how and when the rocks were formed.
There are are several fundamental principles that Earth detectives use as they gather clues about the geologic history of an area. These clues help them establish the relative ages of sedimentary rocks.
As we said earlier, relative age refers to the age of rocks in relation to other rocks. Relative age shows the sequence of formation of a group of rocks, indicating which rock is the oldest, which one formed next, and which is the youngest. But it doesn't assign a precise age in years.
So what is the point of these fundamental principles?
Well, they give you a general understanding of how layers of sedimentary rocks were initially deposited. In other words, they can help you determine when and where each layer formed. Once you know these general principles, you can apply what you know to the rocks and formations around you, and you can really impress your friends with your apparently vast knowledge of geology. Are you ready? Let's look at the Grand Canyon. Go ahead and roll the film.
Oh, cool. Look at the canyon. Okay, so what kind of clues can I get from looking at this?
Well, if you're familiar with the principle of original horizontality...
Okay, wait. What's the principle of original horizontality?
Geologists know that sediments are deposited in horizontal beds. This makes sense, right? As the sediments settle and accumulate on the sea floor, they are lying horizontally. I mean, how else could they be lying? The area that's now this canyon was once under lots of water, and the sediments that settled out of the water formed the layers that we can now see on the canyon walls. As each layer got buried underneath the next and lithified or formed into rock, the layering was preserved, and there it is for everybody to see. So here's the principle of original horizontality. If beds of lithified sediments aren't lying horizontally, then something caused them to move.
Hey, look, there's something on the screen. Hey, it's a sandwich.
A vertical sedimentary rock is a clue that something happened that was powerful enough to move the rock from its original position.
Here's a sedimentary rock that formed lying flat on the bottom of the ocean and which later got turned up on its side. You have to keep exploring to figure out what moved the rock, but the principle of original horizontality gives us the first clue to the geologic history of the area where the rock was formed.
It takes tremendous power to flip big hunks of rock.
Like Hercules.
That rock is far too large. I will move that one instead.
Yeah, like Hercules. Hercules is a geological phenomenon. Besides Hercules, there are a number of powerful other phenomena that can move and flip rocks. These are the same processes like folding and faulting that are at work when mountains are formed. We'll talk in detail about these powerful processes later on in the video.
The next fundamental principle is the principle of superposition. Here's how it goes. If a rock bed hasn't been disturbed since it was formed, you know that it is younger than the layer of rock below it. The layers of rock in the Grand Canyon illustrate this principle as well. See the layers of sedimentary rock piled on each other? Each layer looks a little different, so you can see roughly where one layer ends and the next begins. The top layer is the last one to form. This phenomenon is called the principle of superposition.
So if you want to study the most recent layer of sedimentary rock in an area, study the top layer. That is, unless the rock layers have been disturbed or overturned. If you find a layer of sedimentary rock on top that you know, through absolute or exact dating techniques, is really, really old, then you have a clue that something disturbed the rock layers and flipped them over.
Next is the principle of lateral continuity. According to this principle, sediments are deposited initially in a layer that extends horizontally in all directions.
See how each layer of rock extends out in every direction? The layers thin out and end eventually. This is an example of lateral continuity. The area where the sediments were deposited is called the depositional basin.
It's the law of cross-cutting relationships.
Oh!
And what it is if you see an igneous rock...
Okay, hold it right there, smarty. All right? What is an, as you say, igneous rock?
All right,
what is that?
We'll talk about igneous rocks in more detail later on. But very simply, Igneous rock forms when molten rock, called magma, cools and crystallizes. A cross-cutting relationship occurs when an igneous rock cuts across another rock. Now, they're going to explain, so just watch, listen, and learn.
Here's how a cross-cutting relationship forms. Here we have existing beds of sedimentary rock. And here comes some molten rock, called magma, pushing through the existing rock bed. The magma moves pretty quickly, making its way through existing cracks, forming new cracks, and melting some of the rock it's traveling through. When the magma cools, the new igneous rock cross-cuts the old sedimentary rock.
Youch!
When you have a cross-cutting relationship like this, you know that the rock that was cut through is older than the intruding igneous rock.
Here's a picture of what a cross-cutting relationship looks like in nature. The rock that cuts the bed isn't an original feature of the formation. The rocks on either side of the intruding rock are exactly alike, and the interloping igneous rock, which looks different, obviously shoved its way into the original bed. According to the law of cross-cutting relationships, the intruding rock is younger than the rocks it penetrates.
Here's another generalization that geologists use to deduce facts about the history of rocks. It's a lot like the idea of superposition, but it deals specifically with fossils, so it's called fossil succession, or sometimes it's called faunal and floral succession. You see, since life forms have changed so much over the years, groups of fossils from different time periods will be different from one another.
Like we're different from each other.
We often find fossils in sedimentary rocks, right? So it makes sense that older strata of rocks will have older fossils in them. The principle of superposition says that if the rocks are undisturbed, the oldest layers of rock should be on the bottom. Following this logic, the oldest fossils should be on the bottom too. If we know the age of the rocks, we can figure out how old the fossils in the rocks are. Conversely, if we know the age of the fossils in the rocks, we can figure out how old the rocks are.
The last principle we'll talk about is the principle of uniformitarianism. The principle of uniformitarianism states that you can understand geologic events of the past by observing the geologic events that are going on right now. By geologic events, we mean earthquakes and volcanoes and stuff. According to uniformitarianism, we can figure that a volcano eruption now is pretty much like a volcano eruption was 1 million years ago.
Whoa! Look at that! Did that eruption happen 1 million years ago?
If it had happened 1 million years ago, we wouldn't have it on video, would we?
Yeah, I guess not.
But there can be problems with the principle of uniformitarianism. Variables affecting the Earth's processes have changed through time, so we can't really be sure that the processes we see today happen exactly the same way or at exactly the same rate as they did ages ago.
Let's review. Geologic history is written in the rocks. There's a set of fundamental principles that geologists can apply to the rocks in an area to help them gather information about the geology of that area. The first is the principle of original horizontality. It says that as layers of sediment settle, get buried, and harden into rock, they are oriented horizontally. According to the principle of original horizontality, if a bed of sedimentary rock is not lying horizontally, then something moved it. Next is the principle of superposition. According to this principle, the bottom layer of rock is the oldest in a sedimentary rock sequence, and the layers of rock get successively younger as you get closer to the top of the sequence. The top layer of sediment was the most recently deposited. The principle of lateral continuity says that sediments are deposited initially in a layer that extends horizontally in all directions. According to the law of cross-cutting relationships, an igneous rock that intrudes into a bed of existing rock is younger than the rock it cuts into. Fossil succession, also known as faunal and floral succession, says that the oldest fossils should be in the bottom layers of sedimentary rocks, since those layers of rock are the oldest. If you know how old the rocks are, you should know how old the fossils in the rocks are, and vice versa. And finally, there's the principle of uniformitarianism. According to this principle, you can understand geologic events of the past by observing the geologic events that are happening right now.
Are you familiar with cross-cutting relationships?
Yes, I'm in one now.
Have you ever been cross-cutted?
Not that I'm aware of.
Neither have I.
Don't know anything about it.
Red.
What would that be?
Well, that's kind of what I'm asking you.
Excuse me?
See if you can guess the phrase before time runs out. Here's a clue. This is the process of turning sediment into sedimentary rock. Ready? Begin. The answer is lithification. Congratulations if you guessed it before time ran out.
It's pop quiz answer time. We asked, how old is the Earth? The correct answer is B, 4.6 billion years old. Scientists estimate that the Earth was formed 4.6 billion years ago, about 5 years before Dick Clark was born.